See. Okay, this is the Math 1111 Zoom meeting for 9 p.m. on October 19th. My internet was out from about 11 a.m. to 6:30 p.m. today, so that canceled the 12 p.m. Zoom meeting. So this is the only Zoom meeting for today. We do have a participant. Did you want to see anything?
I guess domain.
Okay. Domain of what?
I think I have a domain of a graph. Let's go with here we go. All right. The polynomial is y equals 3x to the fifth minus 5x cubed plus 5.
Plus 5. You getting this off WebAssign or out of the book?
Off of WebAssign.
Okay.
And then it has -3 to 3 by -5 to 10.
-3 to 3 by, and then -5. Does it look like this?
Yes.
Okay. And so they want the domain?
Yes, domain and range using interval notation.
Interval notation. Okay. Well, your domain is going to be so simple it's hard. They're basically giving you x min and x max when they do this, and y min and y max. So your domain is just going to be this. They've restricted it to -3, 3.
Oh.
Okay. If they did not give any of this, your domain would be -infinity to infinity. There's two problems with domain: fractions where you can divide by 0, or square roots that you got to keep positive. You have neither situation here. There's no fractions, no square roots. So by itself, this would be -infinity to infinity. You understand that? All real numbers?
Yep.
Okay. But when they do this, they're wanting this graphed, or they're using this formula basically on this domain. Now the range, you cannot count on this being the range. As a general rule, yeah, range is y min and y max, but they're going to want the range. This is usually just numbers on the range that they've done to set your graphing calculator. So for the range, we're going to want to punch in -3 to this, get the y value for this, and 3 to this, and get the y value. And that'll be the range for this domain. Did that come across? Or the range, since this is x min and this is x max, okay, to find y min, that will be equal to 3 times -3 to the fifth, minus 5, -3 to the third, add 5. If it works out -5, I'll be very surprised. They generally don't give you any obligation that this would work out. This is just some generic numbers that's supposed to show you the whole graph. Okay, let's see. Three times -3 raised to the fifth. I can put it side by side. Maybe I should clear the screen. Minus 5 parentheses, -3 raised to the third, and add 5. I'm getting -589. The third, but yeah, just the third, add 5. Yeah. Okay, so I don't know, looks good to me if you've punched it along. That's the y min. Let me clear it off. And y max, all right, you'd plug in x equals -3. So you have 3 times 3 to the 5th minus 5 times 3 to the 3rd and add 5. 3 parentheses 3 raised to the 5th minus 5 parentheses 3 raised to the 3rd and add 5. I'm getting 599. So the range should be between -589 and 599. We're using brackets because they use brackets here. That's the way I would do it. You can try punching those in and see if it works. Questions about that?
N-
Have you got any others?
Not at the moment, no.
Okay. Did you want to see an introduction to this week's work, 3.5 and 3.6?
Yeah, sure.
Okay. I'll just put the assignments up. So for this week, yeah, we're doing 3.5 and 3.6. Practice problems for 3.5, 7 to 17, 19 to 35, and 37 to 45. For 3.6, 13 is a long section, 13 to 19, 21 to 25, 31 to 41, 43 to 51. And we will have quiz 8 on Friday, due Sunday, based on these problems. And once again, chapter 3 is pretty much the heart and guts, most difficult stuff of college algebra here. So I did not assign any WebAssign problems this week. You're free to work on them if you want. If you find it helpful and want to do some extra practice in WebAssign, help yourself. We'll get back to WebAssign in chapter 4. I find those a lot more reasonable. Do you want to charge into a few examples from 3.5, or just what are these about?
Sure.
Okay. What we do is 3.5. It's called complex zeros. We generalize to complex zeros. We've done 3.3.4, we've done only real zeros. We generalize to complex zeros. Okay, maybe we should remind everybody exactly what a complex, this means we bring in imaginary numbers. Just to remind everybody maybe what those are, it's been a while since you saw them. If I take a square root of 4, everybody knows I get a 2. If I stick a negative, a square root of 4, everybody know that would make a -2. So negative outside just carries along. Remember what a square root does. This word, we say it's 2, that's because 2 times 2 equals 4. Your answer is the number multiplied by itself, or 2 number multiplied, same number to give what's underneath. All right, your problem comes, here's the problem. Square root of -4. Okay. It can't be 2 times, not 2.2, 2 times, yeah, I missed it all. 2 times 2 is equal to 4, and it can't be -2. -2 times -2 is also +4. You can't use 2 times a -2 to give -4. These are different numbers. So what they did was they defined I equal to a square root of -1. Does this ring any sort of bell? A square root of -4 would then be busted up as a square root of -1 times the square root of 4. -1 times 4 is -4. This is in I. Square root of 4 is 2. They usually write this as 2I. Now here's the deal. I being a square root of -1. I squared is the square root of -1 squared. So I squared equals -1, and it's real. Real means it's on the number line. This comes up a lot. Whenever you see an I squared, you can sub in a -1. All right, let's pause for station identification. Did this ring any sort of bell?
Yep.
Okay. So your general complex number might look like two plus 3I. It has a real part and what's called an imaginary part. You can treat I almost like it's an X. These are unlike terms, they can't be combined. And yeah, they should have some point made you've done some arithmetic with these, like add them, subtract them, multiply them, divide them. I can't really go through it here. But where this section starts, it's called this fundamental theorem of algebra, and I froze. Rats. Is it going to come back? Trying to come back. Okay. Okay, so they're taking a polynomial, saying it has complex coefficients, has at least one complex zero. Okay. I'm not going to write all that gibberish down, but just to try to make it look somewhat familiar, take a polynomial. Hopefully you're familiar with something like that, and you're familiar with how to factor it. X plus 2, x plus 3. It's saying every polynomial has at least one complex zero. Every polynomial has at least one complex zero. All right, a number that looks like this but makes it zero. Well, where is it on something like this? All right, well, notice it says complex coefficients. If I could, man, if it wouldn't keep freezing. Complex coefficients, that means it's got some sort of I part. Well, where is that? Well, you can write these coefficients. Notice there's a 1 there. You could write that as 1 plus 0I x squared plus 5 plus 0I x plus 6 plus 0I. And these are your complex coefficients. Then the zeros come from this. Notice your x is -2 and x is -3. These are your zeros. Well, how are they complex? Well, you'd have to write it -2 plus 0i and -3 plus 0i. Now you got two complex zeros. So you can make, even though it looks like a straight real number, you can make them look complex by adding on this 0i. So what they're going to do is they're going to give you harder polynomials. Maybe we should say more general. That have complex zeros in this section. Are you ready for some examples? This will show you this as well. This conjugate zeros theorem, if a complex number has a zero, its complex conjugate is also a zero. I'll show you where that comes up. That comes up a lot too. You're so odd that I've stunned you into silence. So are you ready to see some examples?
Yeah.
All right, why don't we try with the very first homework then, page 329. This is 3.5. We'll start with number 7. And the p of x is x to the fourth, add 4x squared. And they want you to find, part A, all zeros, real and complex, and B, factor completely. Okay, so very first homework right here. All right, well, you can take a look at this. Whenever you go to factor something, you can think common factor first. Is there a common factor? And sure enough, there is. It's x squared. So we can write this as x squared, leaving x squared, add 4. I'm going to call this factor 1, factor 2. You're setting each one to 0, so x squared equals 0. Square root, so x equals 0. And over here, x number 2, x squared plus 4 equals 0. X squared would equal -4. Square root, and we just did a square root of -4 on the other sheet page. You're gonna, with a square root, you're gonna get a plus and minus, and your square root of -4, square root of 4 is a 2, and with a negative inside, you get an I. Okay, you can read this power and think 4 zeros. All right, well, here's 2 of them. Here's another one, there's 3. Oh no, where's my 4th? Where's my 4th 0? Well, you see, with this x squared, you don't really write plus or minus 0, but you can think of the 0 appearing twice because that's an x squared. But you don't have to write it twice. So really the answer to A, zeros, are x equals 0 and plus minus 2i. And when I wrote this, that's my factor completely. So answer to B, p of x is x squared and x squared add 4. Questions about this? most of the ones on this page can pretty much be factored if you know you're factoring. All right, the next section, they want you to find a polynomial. This is the backwards problem. (37). Find a polynomial degree 2, zeros, 1 plus I, 1 minus I. Are we ready for something like this? We're so stunned we're not speaking. Are you still there? Okay. So, the way we set this up is your zeros are like this. Now this looks a little strange. Remember we said all x-intercepts are zeros, but not all zeros are x-intercepts? So this is a case of that being the same. So our polynomial, if I told you that x was 2 was a 0, you know its factor is x minus 2. Well, you're going to do the same thing with this, except you're going to stick these things in parentheses. So in other words, we're going to have, if that's a 0, the factor is going to be x minus it and 1 plus I. But I got to stick it in parentheses because it's got 2 pieces. Same thing with this, x minus and 1 minus I in parentheses. The rest of this is just nothing but algebra, distributing through, foiling, and boiling it down. It should wind up with a quadratic. Degree 2 will have an x squared, an x, and a number. By the way, if you have an I in the answer, you are screwing up. No I's in the answer. All right, so P of x will equal x minus 1 minus I, x minus 1 add I. All right, let's see. We'll get x squared minus x minus ix. Here's round 1. Now I'm going to distribute minus 1 through. That just will flip signs. Minus x, add 1, minus I. Here's round 2. Notice it's got all the signs switched from this. Minus ix, minus I times negative 1 is a plus I, minus I squared. All right, let's see what happens. Just keep boiling it down, combining like terms. X squared minus x minus 2x. If you want to cross through your pieces. Okay, minus ix and a I think I've got a sign screwed up. My minus I plus I goes away. These should cancel. They're not. Get the same sign, something wrong. X squared minus x That's a plus ix right there. X times I is a plus ix, my fault. See, that's why you got to really watch this. All the i's will vanish. If they don't, you're screwing it, and I just screwed up. Okay, so there's your plus ix minus ix. Now I have a plus 1 and a negative I squared. I squared is equal to negative 1. So I have x squared minus 2x plus 1 minus a negative 1. That makes these alike. That's how you make the I squared vanish with negative 1. 1 minus negative 1, 1 plus 1 is 2, meaning the x squared minus 2x and plus 2. I could check this by running this through the quadratic formula, and I would find my answers would come out literally 1 plus I and 1 minus I. I'll do that. Check. Solve P of x equals x squared minus 2x plus 2 equals 0.
Hey, so my internet dropped.
Oh, okay.
I just got back.
Okay. Should I go back to the beginning of what I was doing?
No, I'll pick up from here.
Okay. Basically, I was working problem 37, which is basically the reverse problem. Find a polynomial degree 2, and it's got these zeros. So maybe just to catch you up, you know, if I had just a straight number with a 0 from the last two sections, its factor, you know, is x minus 2. You go x minus the number, because plug in 2 minus 2 will be 0. So you do the same thing here. If these make a polynomial 0, then I literally go x minus that and x minus that. But I got to stick them in parentheses because they got multiple pieces. All right. The rest of this is foiling all out. And if you wind up with an I in the answer, you're screwing up. All the i's will vanish. So I distributed through the minus signs, minus 1 minus I there. Then you get a minus 1 and plus I there. And then it's just a matter of distributing. I would distribute each piece in this through the second one. So x times x is x squared. X negative times negative 1 is negative x. And x times I is xi, or you write it ix. Minus 1 times x. Minus 1 times negative 1, positive 1. And minus 1 times I is a negative I. And finally, a negative ix. Negative I times negative 1 is a plus I. And negative I times I is a negative I squared. All right, you see an x squared there, and minus x is negative 2x. Ix minus ix is 0. And there's a negative I somewhere. Yeah, negative I plus I, that's 0. You wind up with this 1 minus I squared. Well, I squared is negative 1. Anytime you see an I squared, you can put in negative 1. Making it 1 minus negative 1 is 1 plus 1, which is 2. All right. What I was about to do when you just came in, that's the polynomial that'll have these zeros. I like to check the first one. What I was going to do is run it through the quadratic formula and show that you get these zeros back. Have you got the patience for that, or do you believe?
I believe you.
You believe, okay. You want to see something further down the page?
Sure.
Okay, well, they give you, like I say, a whole nother section of those, and some of them are more like projects than problems, the degree 3s, degree 4s. And then you get some of these kind of nasty polynomials here. They want you to find all zeros. So some will be real, some will be complex. You're going to have to start with that theorem, list of all possible zeros. You got that far where you did factors of the end over factors of the first. What would you like to see?
You pick.
Me pick? Well, how about something like 49?
All right.
Okay. Now, you know how many zeros, it's always helpful to know how many zeros you're looking for. So it's off page 330. 49, p of x is x cubed squared, add 2x, subtract 1. You know how many zeros we're looking for? 3 zeros. Highest power. If you know that, then, you know, if you miss one or what, you know, stop short of 2 zeros or 1 or whatever, you know, hey, I'm missing a couple zeros here. Okay, are we ready to get started?
Yep.
All right, list of all possible zeros. Did you get that across? I think we covered that in 3 maybe. And P over Q, factors of -1 over factors of 1. This is the end number. This is the lead number. So this will be like plus minus 1 over plus minus 1, which is really just plus minus 1. When 1 divided by 1 is just 1. So I'm really only getting 2 possible numbers out of that. Did we get across how to look for these on the calculator? I literally could just plug it in. This is simple. I literally could plug in 1 here, see if I get 0, or -1 and see if I get 0. But I showed everybody on the calculator, if you'll punch your formula in, x to the third minus 2x squared, add 2x and subtract 1. Go to the window, table set. Well, yeah, we're on auto. This will punch everything in automatically. And then I go to table at the end. Okay, I'm not getting anything. It's literally punching in these x numbers into that formula, that polynomial formula in the problem that I entered as y1. Can you tell going up this way, things are just getting more negative. So I'm really not getting anywhere. I'm looking for zeros. -1, 0. Aha, x equals 1, I hit. And that's the only one I'm going to hit. At x equals 1, I get 0. I don't know, did we get that across? We had a shortage of Zoom sections last week. Okay, so you know this means it has a factor of x minus 1. So this means I have x cubed minus 2x squared, add 2x, subtract 1 can be written with an x minus 1 times crap or junk. I guess the technical name for it is quotient. Are you with me so far?
Yes.
Okay, so in other words, I could stick 1 on this side, I get 0, and then 1 there, minus 1, I get 0. So you understand how we're going to find the crap?
Yep.
Got to divide both sides by x minus 1. This will cancel, and this is called the quotient. This will be the quotient, QUO quotient that comes out. This is why we did that long division section. Or you could do it by synthetic, since that's first power, if you like synthetic. I don't know how long this is going to be, so let me go ahead and start on the next page. So we're going to take x minus 1 and divide it into q minus 2x squared, add 2x, and minus 1. So x into x cubed goes x squared. X squared times x is x cubed minus x squared. Subtract, put this in parentheses. X cubed cancels. -2 minus -1 would be a negative x squared, add 2x, subtract 1. X times negative x squared. By the way, this will go evenly with no remainder. Should have mentioned that. If it doesn't, you're screwing up. This will divide evenly with no remainder. If not, you're screwing up. It's good to know what's supposed to happen. So if I wind up with a remainder, I know I messed up. All right, so x into negative x squared, negative x times negative x squared, add x, subtract, x squared cancels, 2x minus x would be an x minus 1. X into x one time, multiply back, x minus 1, subtract. Do you see that I get a 0 remainder?
Yeah.
Okay, so you understand this is the crap, the quotient.
Yeah.
So x cubed minus 2x squared, add 2x minus 1. Basically, I factored it as x minus 1 and x squared minus x, add 1. Now, I could check this at this point if I wanted. If I foiled all this back, it should come back to this. Do I need to do that, or do you believe?
What the heck? I want to see it.
You want to see it. Got it. If it doesn't work, I'll quit on the spot. I get x cubed. I'm distributing the x through. Minus x squared, add x. Then minus 1 just switches all the signs. Minus x squared, add x, and minus 1. Which gives me x cubed minus 2x squared plus 2x minus 1. Is that what I got here?
It is indeed.
It is indeed. In other words, remember, your quotient times your divisor equals your dividend when there's no remainder. Okay, so what's the point? We got to find the other two zeros. Okay, because we know the first 0 is x equal 1 from this. Remember, if you set this to 0,
Yeah.
you get x is 1, and we knew that from the first. Well, we got that off the calculator by plugging from the list of all possible zeros and plugging in the calculator. All right, this is a quadratic, so the absolute easiest thing is quadratic formula. So number 2, x squared minus x add 1, use quadratic. If I really wanted to be a formula, I can't spell it, formula. If I really wanted to be anal, I'd repeat the whole thing. I'd find my list of possible zeros, plug it in the calculator. It'd be we'd be here forever. So when we get it down to a quadratic, the simplest thing is quadratic formula. So that's x equal, your negative b will be 1. X square root, your b squared will be 1. minus 4 times 1 times 1, 4ac, over 2a will be 2. That's going to be 1, add and subtract the square root of -3 over 2. And we usually like to write this with an I, and there is no root 3, even, nice, clean root 3, so we just leave it root 3. In other words, we'll write it 1 plus or minus I root 3 all over 2. All right. So you could spread this out. 1 add I root 3 all over 2. 1 subtract I root 3 all over 2. These are zeros. If I plugged them in the original, I'd be here forever trying to show you that. If you want me to, I'll take the next 30 minutes and do it. But literally, if I plug these in to this, I would get 0. But they are not x-intercepts on the graph. This is an x-intercept on the graph. So all x-intercepts are zeros, but not all zeros. These are zeros, but not x-intercepts. On the graph, what turns out, the graph will hook and like won't come down to the axis like this. That's what will happen. Do you want to see one of these plugged in and show it really gives 0, or do we believe?
I think we believe.
Okay. Well, that's the kind of stuff they make you do. That pretty much covers an example of everything in this section. We're at 46 minutes. Did you want to see anything from 3.6, or have we opened up your head and poured in enough today?
I don't have anything else to do today.
Okay. Well, 3.6 is about graphing rational functions. There we are. We see the word rational, think fraction functions, and filling in a worksheet about them. They're going to want you to find asymptotes. You know what those are?
Yes.
Okay. There's vertical and horizontal. Vertical is
Slanted, right?
what now?
Slanted, right?
We won't be messing with slanted.
Oh, okay.
Just vertical and horizontal. The horizontal, this one's kind of nasty. Vertical is pretty simple. They want X and Y intercepts. I believe they want domain and range. Let's see if I can find my assignment sheet. Yeah. Uh, 13. So I asked for like pieces of it. They bust this into a lot of pieces. They don't want everything on every piece. But here's 13 to 19, 21 to 25. Okay, that's the next one. 31 to 41 jumps over to, okay, so 31 starts at the bottom. 31 to 41. 43 to 50. Well, okay, so these are real projects, so I busted it in half. Don't thank me all at once. 43 down to like 51. And they pretty much want the whole thing. Intercepts, asymptotes, domain and range. Well, I get, okay. Yeah, they want the whole thing. X and Y intercepts, horizontal, vertical asymptotes. Notice how plural they are, then sketch a graph and domain and range. So they want the whole thing on these last parts. They're just asking for part of it on the others. Okay. guess we'll just start in on the first one, page 344, 13. R of x, 1 over x minus 1, and they want domain and range. Okay. It tells you to use transformations of this graph 1 over x. You don't have to mess with that. You can use the calculator. Graph on the calculator. So if I go to the calculator, that off, and I will want to put this in parentheses. Get the whole thing on the bottom. 1 divided by parentheses, x minus 1. Good window, graph. Okay, you're going to get a series of these little curves. All right. Notice that this kind of comes over and bends down. And you got something up here bending down to this. All right. I don't know if you notice, see that first tick mark? That's going to be 1. In other words, this graph is bending to 1. Now, do you see where the 1 comes from? Look at your bottom, and you see where it is blowing up, so to speak. Send that to 0, your x equals 1. This is what you can't use. It makes you divide by 0. You'd be going 1 over 1 minus 1, which is 1 over 0. And that's what the graph is telling you. So the graph is coming along and bending at 1, and then it's bending against 1 here. And see how it never crosses 1. This is in effect, didn't ask for it, but this in effect is your vertical asymptote. So you see how to write this domain? It's basically your fraction problem. You don't really need the graph to write the domain. You can't use 1, so you're going negative infinity to 1, 1 to infinity. Questions about this?
Nope.
Okay. Now you do need the graph for the range. Remember, a range is y min, y max. Well, your minimum y, you see this goes all the way forever down. That's negative infinity. Now notice how they bend at 0. This is the x-axis. This is y equals 0. It's bending below there, and it's bending to it here. It never crosses it. So you really can't tell you're not using 0. But you really can't tell that unless you actually see the graph. So you go to 0 and 0 to infinity. And notice I'm using parentheses, both cases. Can't use 1 in the domain, makes you divide by 0. And the output never hits 0. And this is all they're asking for here. Questions about that?
Nope.
All right, 21, they zero in on intercepts. R of x, you have x minus 1 over x plus 4. Find x and y intercepts. Okay. On an x-intercept, if you remember, the other letter is 0. This is the y. So you're sticking 0 equals x minus 1 over x plus 4. All right, so you can multiply both sides by x plus 4 times 0. X minus 1 over x plus 4 times x plus 4. So that kills this. So in effect, and 0 times this is 0. Then you add 1, and 1 equals x. This is your x-intercept. X equals 1. Your x-intercepts come from where the top equals 0. Always. Because you see, if I stick in 1, 1 minus 1 is 0. 0 on top gives me 0. All right. At your y-intercept, the other letter is 0, which means y then is 0 minus 1 over 0 add 4. I stick in 0 for x. I'm going to get negative 1/4. That's my y-intercept. Questions about this?
Nope. We're good.
Good. Okay. Go down to 31, and they want horizontal and vertical asymptotes. Give you r of x, 5 over x minus 2. All right. The vertical one is easy. Set your bottom equals 0. So x minus 2 equals 0. X would equal 2. That is your vertical asymptote. This graph will blow up at 2. I can show you that from that very first one, 13, as well. I wrote it down. See, you're setting your bottom to 0. Didn't ask for the vertical asymptote here. I want to set to the bottom to 0 and get 1. Notice, I put it, that's, the graph is blowing up. The lines will bend to that number. Questions about that? All you got to do is set your bottom to 0 for a vertical asymptote. The horizontal, much trickier. Look on page 336. And look at this gibberish. I'm not going to write this gibberish down. All right. Number one, they're giving you vertical. Yeah, and they're telling you set the denominator equals 0. A is a 0 of the denominator. Okay, so that's where they're giving you, in number one, they're giving you vertical. 2, you got to compare what they're doing. This is your horizontal asymptotes. They're comparing the powers. And then there's 3 cases. So let me just write in, let's say I've got, just for an example, a polynomial, and I've got an x cubed plus an x squared. It doesn't matter what the other terms are. All right. And on bottom, I've got, this is, say, case 1. They're calling it case A. Let's say I've got an x to the 4 plus an x cubed. Okay, blah, 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 blah. I'm trying to fill in some numbers, make their gibberish a little more understandable. This is a case of top power less than your bottom power. Your horizontal asymptote will be y equals 0, which is the x-axis. Okay, that's what they're saying. If I put this back under the camera. They're comparing the top power, they call it top power N, the bottom power M. And your top power less than your bottom power, you will automatically be y equals 0. X-axis. Okay. If the top power equals the bottom power, they're calling it case B. Top power equals bottom power. That would be like having a 3x to the 4th over a 4x to the 4th. And you have other terms, but you only care about the lead. Your horizontal asymptote ratio of lead coefficients, meaning it would be y equals 3/4. Lead coefficient over on the top over the lead coefficient on the bottom. That's what they're saying here. AN over BN, that's the lead coefficients, what they're calling them. Do we need to pause for station identification? You got to kind of memorize these three cases. Are we losing you or any questions? Are you ready for case C?
I think so.
Okay. Case C, the only thing left is your top power greater than your bottom. That's pretty easy, actually. Top power greater than bottom power. This is easy. No horizontal asymptote. That would be like having reverse this 4x to the 4th over, let's say a 3x to the 3rd. You have other pieces. And there'll be no horizontal asymptote at all. And that's what they're saying. Top power on top, ends on top, greater than bottom. No horizontal asymptote at all. Okay, back to 31. See which case 31 matches. There's an x to the 1 here. I don't know if you remember, a number is degree 0. You can always write an x to the 0. So your top power is less than your bottom power. That's a case 1, or A here. It's y equals 0. Your horizontal asymptote, y equals 0. I could show you these from the graph. You want to see a graph of this and how you pick them out? Because you can always graph them and pick it off the graph as well. You want to see a graph?
Sure.
Okay. So I don't have to enter the x to the 0. We had 5 divided by parentheses, x minus 2. Make sure you stick that x minus 2 in parentheses. Okay. See if you can spot. See how your horizontal asymptote is going to the x-axis. Right. And then your vertical asymptote, it doesn't show you this. That's why it's kind of important to be able to pick it off the formula as well. But yeah, x equals 2 is that vertical line. The vertical line is going right through x equal 2. So these lines are bending to x equal 2. Questions about that?
Nope.
You want to see one last one where we put, oh, we're over an hour and 5. Whoa, okay. Time flies when you're having fun. You want to see one last example that puts it all together? They want the whole thing?
Yeah, sure. We can do one more.
Okay, so that's page 345 at 43, say. R of x, 4x minus 4, x plus 2. They want the whole thing. Wish they separated off in parts. Intercepts. I'll come down the page. Asymptotes. Want a graph. And then they want domain and range. Here's kind of the worksheet of it. They compress it back into one paragraph. Here's what they want. Intercepts, asymptotes, sketch a graph, domain and range. The reason they do the graph, now you need the graph to be able to do the range. You can do the domain right off the formula if you know what to look for. So I might fill it in with not in order here. You see how to write the domain? You've got a fraction problem. You can't use x equal -2. You'd be dividing by 0. So on your domain, you have -infinity. If you wanted to graph it, -2, you'd have an open circle. -infinity, -2, -2 to infinity. Questions about that? All right. And by see, domain and vertical asymptote are basically the same thing, meaning you can't use the x equal -2, so that's your vertical asymptote. Your vertical asymptote is x equal -2. This is your vertical asymptote. Okay, if you want to do it back in order, at your x-intercept, y equals 0. So you're just going 0 equals 4x minus 4 over x plus 2. You only care about the top. 4x minus 4 equals 0. 4x equals 4. Divide by both sides by 4, your x would be 1. So that is your x-intercept. And your y-intercept, x equals 0. So y would be 4 times 0 minus 4. 0 add 2. Looks like you get -4 over 2, which would be -2. And that is your y-intercept. Should we pause for station identification? Are we going too fast? Okay, let's get a graph, and off the graph we can read the range. You want parentheses around both top and bottom here. Parentheses 4x minus 4, parentheses x plus 2. Window graph. Okay, so this is why it's kind of important to know what you're doing. It's hard to see where you're blowing up over here straight off the graph. That's why it's very important off the formula. You're blowing up at -2. Even though on this kind of window, to really see it, this is really approaching -2, but I have to see a much bigger Y max to see it approaching. You can kind of see it off of here. You can see -2. It's really blowing up at -2 there, and it would be doing the same thing here. And I could see it better if I increase the Y max. So I'm really at -2. I've got my vertical asymptote, and I am blowing up. Now, here's the other rub. Your horizontal asymptote. All right, well, what case is it? You got to know which case. Remember, there's 3 cases. Well, you got an X there and an X there. Your top power equals your bottom power. If you remember, that means your y is equal to 4 over 1. 4 there, 1 there. Ratio of lead coefficients. Lead coefficients. So really up at 4, you've got a horizontal asymptote. So over here, this piece is doing this. And here, your piece is doing this. It's approaching -2. It's crossing at the y-intercept at -2. You can see that. So it's approaching 4. You almost see it approach 4 there. Okay, can you tell your range? Starting -infinity, but you really can't use this horizontal asymptote. That's the number that gets excluded. So you're going up to 4, and then from 4 to infinity. That's a lot of detail when you throw it all together. Did we lose anybody or lose you? Or...
Nope.
Okay. Yeah, that's the kind of stuff you got to keep straight when they throw it all together, all in one problem. All right, about an hour and 11 minutes. That's a long time. Appreciate you coming out this late on a Monday night. Is there anything else you want to see?
Nope, that'll be all.
Okay, that's pretty much about everything for this week. We'll try to hold 2 more Zoom meetings at 12 and at 9 on Thursday. Hopefully, having some bad luck with the Zoom. Well, I had to cancel at least Mondays last week, and then internet problems today. But we got a good session in today. So if you don't need to see anything else, then I'll go ahead and let you go. We ready to end?
All right.
Appreciate you coming out. Thank you very much.
All right. See ya.
Okay, see you.